I wanted to do a video voiceover of section 4.2 for your review. We're looking at natural exponential functions, talking about the number e and the natural exponential function, and continually compounded interest. Any positive number can be used as a base for an exponential function. We saw that in section 4.1. But in this study, we're going to study a special base, e, which is a convenient for applications involving calculus. Now, e is a number. The number e is defined as 1 plus 1 over n, all to the nth power, approaches as n becomes large. In calculus, this idea is made more precise through the concept of limits. And the table shows the expression for an increasingly large value of n. Now, this bottom number down here is kind of like how we can round 2.71828. Similar to when you look at pi, which is 3.14159, and it is an irrational number that continues on and on, which is why we give it the symbol of pi. So here is 20 decimal places of e, and again, it is an irrational number, so it doesn't end and it doesn't repeat. The number e is the base for the natural exponential function. Why we use such a strange base? Well, it might seem at first like such a base as 10 might be easier to work with, but we see, however, that in certain applications, the number e is the best possible base. Similarly, when we look at circles and we discover that pi is able to be used as the best possible number for looking for circumference and diameter and area, the same as with E. So it was discovered that this number works well in a lot of applications. So in this section, we'll study how E occurs and the description of compound interest. So the natural exponential function is f of x equals e to the x. And here we have a graph. We already looked at some of these before when we looked at y equals 2 to the x, sorry about my crazy circle, and y equals 3 to the x here. We can see that, actually, it looks like I'm pointing at the other one, so let me erase that. Let's do a better drawing. Y equals 2 to the x here. Okay, here we go. All right, and then in the middle, you can see between 2 to the x and 3 to the x is e, which is 2.71828. So you can find this on your calculator if you look for your e to the x button, and we can evaluate. Here's 3 examples. E to the 3 is 20.08554 approximately. Again, these are all approximate, and they're approximate because we're dealing with irrational number. And e to the 4.8 is 121.51042 approximately. So interesting that we have infectious disease example beginning to spread in a small city of a population of 10,000 people. After T days, the number of people who have succumbed to the virus is modeled by this formula. How many people are there initially affected at time equals T? Time would be 0 because that's your initial value. There has not been any time that has gone by. So if you make that 0, then you're going to solve. This would be 0, and then e to the 0 is any number is 1. So you're going to have 5 plus 12, 45 on the bottom and 10,000 on the top. All right, let's take a look. And then we want to look at the graph. So as I said, you're going to put 0 in for the value of t, and you will get 8. And so we conclude that 8 people initially had the disease. If we look at 1, 2, and 5, we can round off the following infected people: 21, 54, and 68. We certainly have learned how quickly that we have infectious viruses or diseases can spread. Okay, from the graph you can see here that once we have the infected people, that it will start to rise very quickly, and then it kind of levels out. Now we can also use this for compound interest. So we have A of t equals P times 1 plus R over N, all the quantity here to the NT. And we're going to take a look at this breakdown. So as M becomes larger, the quantity approaches the number E. And the amount then can be reduced to be P times E to the RT. So you can see here, again, the definition for E follows this form. So that's why we discover that we can actually replace that with E. So here we have the compounded interest. We have A of t, which is the amount after t years, the principal, the interest rate, and the number of years. Here's an example. After 3 years, if you have $1,000 is invested and an interest rate of 12% per year, what is the value compounded continuously? So we plug in the amount for P is 1,000. The rate is 12.012 for 12%. And we're looking at 3 years. So we plug the values in and we see that compounded interest then would be $1,433.33. And that is all for section 4.2. So I will see you next time for section 4.3.